functions themselves. Okay, so whenever you write an exact differential in the partial derivative form, this is what we need. So this is pressure as a function of temperature and volume. We could also add in the number of moles. We'll do that later, but not for the state, or not for the equations of state. Okay, so for an ideal gas, we know from lecture 3 on Thursday last week that this exact differential, you can replace those partial derivatives with the actual partial derivatives that you take from the ideal gas law, and you get a function that looks like this. And if you do the van der Waals gas, you get a function that looks like this. And these are nice, but they're not general. Okay, so both of these equations are specific, dependent on the equation of state. So if we want this to work as a mathematical formalism, it must be general. We must be able to use the expressions we derive for any gas, regardless of the equation of state. So it's useful to define the dependence of the volume on temperature and pressure as follows. Okay, so these are new definitions. The first one, which will use symbol alpha. Sometimes this is written as beta in textbooks. And this is the expansion coefficient. It's also the isobaric expansion coefficient. It's in units of inverse Kelvin, or 1 over Kelvin. Beta is sometimes used. Why do you divide by volume in front? Okay, we stated in here and reinforced in discussion that this partial derivative is the dependence of the volume on temperature at constant pressure. You divide by volume here because you want these to be table values. So they need to be intensive. Volume is extensive, so that's why you divide by volume. So this is the intensive quantity. It's specific to the gas, and it's a table value. So this is something that can be measured. Okay, now we need the dependence of the volume on the pressure, and so this is known as the isothermal compressibility. And this is always written as kappa. Sometimes the sub T is written, sometimes the sub T is left off, but kappa always means the isothermal compressibility. Okay, so this is the dependence of volume on pressure at constant temperature, and it's the intensive quantity. That's why you divide by volume. Notice that it's negative y. Makes some sense, but why? What happens when you squeeze on a gas? The volume goes down, right? So dV is negative, and so multiplying by a negative sign out front makes kappa positive. That's why. Okay, so then I did this from the Euler chain in the previous lecture. So I showed you using an Euler chain with the state variables that the partial derivative of pressure with respect to temperature at constant volume could be written as this ratio. Okay, why did I write it this way? Because now we have definitions for those partial derivatives. We have them in terms of kappa, in terms of alpha. Okay, so then the partial derivative of V with respect to T at constant pressure we get from the top equation. That's just alpha times V. And then likewise minus kappa T times V for the derivative of dV dP at constant T. Okay, so then we got a factor of volume in the top and bottom. We cancel that. And the negative signs also cancel. And this just becomes the expansion coefficient divided by the isothermal compressibility. Slick. Why is this important? Well, now we can go back to our exact differential and plug in values that we can get from a table that are now general. Okay, so first, in order to do this, we have one, right? Let's see if I can get it in the right direction. So we have dP dt. Now we need dP dV. Okay, so we have this one. Now we need this one, but we can get that from the definition of the isothermal compressibility very easily. So we multiply both sides by volume, negative volume, and then invert it. Okay, so now we can plug this all back into our partial or our exact differential. So this is what we started today's lecture with. And we showed that we can write this total derivative specifically for an ideal gas and for a van der Waals gas, but we wanted a general expression. So I'm going to give you a general expression now where instead of a functional form that goes in place of the partial derivatives, it's going to be functions of the isothermal compressibility and the expansion coefficient. Okay, table values, values that can be measured. This is true for any gas, ideal gas or otherwise. Notice there's a factor of volume in there. How are we going to deal with that? Well, what this expression gives you is it gives you the incremental change in pressure with an incremental change in both temperature and volume. And because this is an exact differential, if we want to know the total change, that is a finite change rather than an infinitesimal change, we can integrate this function. We can integrate the first term with respect to temperature and the second term with respect to volume. Okay, so this is the same expression we had before. Now we integrate it to find our finite change in pressure with a change in temperature and volume. So we start out at some initial temperature, some initial temperature and initial volume, and we go to our final state, some temperature final and volume final, and now we integrate these functions. Okay, so if we want to do this right, we'll have to know the dependence of alpha on temperature as well as the dependence of K or kappa on temperature. So initially we'll just assume that those are independent of temperature and that kappa T is independent of volume. So if those are all constant, then we can just integrate, right? And the first one integrates dt from T initial to T final, that's just delta T. The second one we have to integrate dV over V, which is the natural log. Straightforward. So if we can get our table values and we assume that they're constant, then for any change in temperature and volume, for any gas, we can get the change in pressure. That's why this mathematical formalism is useful, at least for this. We'll do something similar for just about every state function. Okay, so before I go on, you guys had to use integral tables in the last homework assignment. And so if you go to some standard text, or standard text meaning a CRC handbook of chemistry and physics, and you find a mathematical integral table. I'm not sure if this is published in Abramowitz and Stegen, which is another table values of mathematical functions. You can get them online, right? Remember, mathematicians don't like log base 10. So they will write LOG, meaning natural log. So if you didn't know that, now you do. If you look at an integral table, you'll find that function written as log of VF over VI. But because chemists use log base 10, I will make the distinction. All right, so we move on. Yeah. If you need to use them on an exam, yes. Absolutely. Anytime you need to integrate a function, you're welcome to use an integral table, right? And if it's something that you can't integrate readily from your own experience, that is, the natural log better be something you can look at and integrate. Polynomials, straight polynomials, not 1 over the polynomial function, But a straight polynomial function you should be able to integrate without an integral table. Everything else you can use. Okay, so now we want to do the same thing for the two state functions that we know. We have a state function of internal energy U and a state function for enthalpy H. Okay, so in order to write this in our total derivatives, we need variables. And so we're free to choose what variables we want. Okay, so we need to be smart or clever about our choice of variables. And since we know that the partial derivative of U with respect to temperature at constant volume is the heat capacity, maybe volume and temperature are good ones to use for U, and likewise for the enthalpy H, since the partial derivative of H with respect to T at constant pressure is the heat capacity at constant pressure, then maybe pressure and temperature are the right ones for enthalpy. And those are good. Those are good choices. There are others, and we'll come back to them maybe in a week or so. But let's, for now, assume that we have V and T for U, I wrote it as T and V, and P and T for H. Okay, so right away, we can write these total derivatives. Okay, but since U and H are state functions, we can write the exact differentials of U and H. We can choose V and T as the variables for U, and P and T for the variables for H. Okay, so here's the exact differential for U. And here's the exact differential for H. This does not depend on ideal gas, a liquid, a solid, a chemical reaction. This is a general expression. Okay, so I'm going to try and manipulate this generally, but in order to do some examples, I may have to switch over and say, let's assume we have an ideal gas. So you need to pay attention when I do that. Which ones are general and which ones are specific. Right now, completely general. Okay, so first we'll look at the exact differential for U, and then we'll come back to enthalpy. Okay, so here's the same expression for U. Now, in order for this equation to be general, in other words, one we can integrate like we did for pressure to get the changes in internal energy. And the first law of thermodynamics talks about changes in internal energy, so that might be a useful quantity. We need to know what those partial derivatives are. Okay, so we've already seen that the initial one is CV. Okay, I'm going to prove it. I told you it was before, but I'm going to prove it. Okay, so let's first look at the first law of thermodynamics. We know that the first law of thermodynamics says that an infinitesimal change in the internal energy is equal to infinitesimal work plus infinitesimal heat. Notice that I've used the small deltas for Q and W. I've done so because these are not exact differentials. But I do know what they are, right? If I assume only mechanical work, then I can replace the incremental change, the incremental work as minus P external dV. And now dV is an exact differential, so I can use the small d. Okay, so now I want to start looking at what happens if I hold one variable constant and one and let it vary with the other. Okay, so maybe a good one to choose would be volume. Okay, so we'll look at both of these separately. So we assume constant volume, and now we can obtain an expression for du dt at constant v. So this is the same expression from the end of the previous slide. Okay, so now if we hold volume constant, two terms, one on each side will drop, right? Constant volume means dv is equal to 0. In other words, no change in volume. Okay, so that means the p external dv term on the left is going to drop, and the partial derivative of u with respect to v at constant t times the quantity dv will also drop. And we're left with now the incremental heat, and because we're talking about constant volume, I'll write this sub v. Okay, so this is an expression that we had before, right? We said that the incremental change in heat at constant volume with an incremental change in temperature is equal to CV. And so this is what we know from our discussion of heat, right? We knew that it was proportional to the change in temperature. So therefore, CV dt has to be equal to the partial of U with respect to V, or to T at constant V dt. And therefore, those have to be equal. So CV is going to be equal to du dt at constant V. And that's a formal proof. Okay, so last line of the previous slide.
du is equal to CV dt.
So this is a formal proof of the above expression, which we already knew. Okay, so now we can plug in CV for partial of U with respect to T at constant volume. The other thing is this is completely general. Okay, so there it is. So we go back to our initial expression using the partial derivatives. And now we've shown that the partial of U with respect to T at constant volume is CV. So now we need the other derivative. Okay, and we need to talk about what this is, and then we have to be clever about how it's measured. Okay, so it's this partial derivative that we're after next, right? The change in internal energy with a change in volume and constant temperature. Okay, so this is done experimentally. In a way, this was done experimentally too. The experiment was calorimetry. We said that an incremental change in heat is proportional to an incremental change in temperature. And that's the proportionality constant. Okay, so how do we measure this partial of U with respect to V at constant T? Well, this was done by our old friend James Prescott Joule, Brewer physicist. Okay, this is one of the experiments that he did. And what he was interested in is he said, well, what happens if I take a gas confined in some space and I let it expand into a vacuum? Okay, we'll generalize it to high pressure to low pressure in a minute, but he had a way of evacuating one side of a glass, of a piece of glass where two chambers were separated by a valve. Okay, and he said, all right, well, if I want to measure, and he knew that there was a mechanical equivalent of heat. Okay, this was his premise, right? So what he's going to do is work in this case, because the volume is going to double. So he'll do work, and he wants to know if he can convert some of that work into heat. Okay, and so how is he going to measure this? Well, he's going to measure it as a change in the temperature of the water bath surrounding this thing. So in other words, we have a calorimeter. So we set up this experiment. We have some initial conditions. We have the pressure inside of the left-hand side, some initial volume, and the temperature, which is now at thermal equilibrium with water bath. So the temperature of the water bath is the same as the temperature inside the gas. Okay, so then the valve separates the high pressure from the vacuum, and when it's opened, then the gas expands into a vacuum. Okay, now, gas expanding into a vacuum said, oh, no work. Right? Because my external pressure is 0. Okay, so then there must not be any heat, right? And his measurement showed that, so here's the expansion into the vacuum, so now we have the final pressure and final volume is double what it was initially. Okay, the final pressure is of course less than the initial pressure. And then the temperature was measured and there was no change in temperature. Oh, delta T is equal to 0. No work converted into heat here. And so from the first law of thermodynamics, we have this equal to 0. And what happened here was no temperature change was measured. And so Joule's premise was this was done at constant internal energy. Makes some sense, right? No work, no change in temperature, no heat, no change in internal energy, constant internal energy. So therefore, we know when we have constant U, we can write partial derivatives, right? So the measurement was this one. An incremental change in temperature for a incremental change in volume at constant internal energy has to be 0, right? Okay, this was constant temperature because when the volume was doubled, this was 0. Therefore, and this was done at constant internal energy because there was no change in the internal energy, no work, no heat. So therefore, this whole thing has to be 0. Okay, this is not the derivative that we were after, right? The one we were after, let's remind ourselves, was that derivative. Okay, but if you're clever and you remember your mathematics, most importantly, an Euler chain relation gives you all of the partial derivatives of those nested 3 variables, right? The 3 variables in that derivative are t, v, and u. Same 3 variables of this one. So we have a shot at it. We can use an Euler chain relation and solve for that one. Okay, so the first one we start with is the one we want. Okay, and then we do our Euler chain relation. So V is on the bottom of the first one, it becomes the top. Then T goes in from being constant to being the derivative we take, or the variable we take with respect to, then U becomes constant. And then we do the cycle one more time, T on top, U inside, and at the bottom, and that's equal to -1. Okay, so that's the one we want. This one, inverted, right? The inverted derivative here is the one that was measured, this one, in the Joule expansion experiment. And then this one, we don't know what to do with, okay? So let's see where we go. Solve for the one we want, which is du dv at constant T. Actually, this one we do know, right? This is the inverse of the heat capacity. Yes?
Yep. Nice.
Okay, so now we invert both of these partial derivatives. So all we did here is divide by the product of these two to this step. Then we invert both of these. Now it's T, dt, dv, constant U. That was the measurement that we just made. This one is the heat capacity at constant volume. So we plug in the heat capacity at constant volume for this one. And then we have this value times dt, dv at constant U. And now we know that this one is equal to 0. So that's going to make this equal to 0. CV can be non-zero. And it has to be always true based on the experimental data. Okay, so this is what the experimental data said. We know that at least part of the time CV is not equal to 0. And so that means that with these two things true, du dv at constant T has to be equal to 0. Okay, it turns out, and I'll show you why, that Joule's experiment was flawed and failed to measure the very small temperature difference that occurred when the gas expanded. Where does that energy come from? It isn't coming from work, right? Because no work is done. We are expanding against a constant external pressure. If we have a temperature difference, where does the work come, or where does the energy come from? What's being converted into heat when you expand into a vacuum?
Friction?
What's that?
Friction?
Not friction.
Energy of the wall.
Why?
Wait, which?
The atoms themselves, why?
Oh,
Because when they're closer, because of like the KEP curve in the molecular,
When they're closer together, they're what?
they
Have an attraction or a repulsion, right? Okay, so if you have gas particles that are described by a real gas rather than an ideal gas, they have some interaction energy, and that's what supplies the heat. So if the temperature goes up, then those gas particles are attracting one another because you're expanding, making space between them. If the temperature goes down, and this happens, then that means those gas particles were repelling one another, and so going into a larger volume is better for them. Okay, but Joule's experiment wasn't good enough to measure it because he didn't have accurate thermometers. Not surprising, right? Anybody know when the thermometer was invented? Early 1800s, early 19th century. By then, thermometers were readily available, but not accurate. So Joule's doing this in the mid-19th century, these experiments, 1830s to 1850s. He doesn't have an accurate thermometer, and he has a very large water bath. He doesn't measure this very small change in temperature. Okay. So this is true only for an ideal gas, and it's true for an ideal gas because in an ideal gas we say that the particles don't interact at all. Okay, so this is specific for an ideal gas. Partial of U with respect to V at constant T is 0. So also valid for ideal gases are the following. So change in internal energy with respect to volume at constant temperature, that's the one we are discussing. That's equal to the partial of internal energy with respect to pressure at constant T, and it's related to the enthalpy, the dependence of the enthalpy on volume at constant T, and the dependence of the enthalpy on pressure at constant T. All of those are 0 if you assume an ideal gas. That's useful to remember. Okay, so then for real gases, we're going to need a better functional form. And in order to do this, we're going to need a better experiment. That comes later. Okay, so for real gases, we write that the limit as the pressure approaches 0, this quantity partial of U with respect to V at constant T is approaching 0. This quantity is known as the internal pressure. Okay, so in general, now we're back to in general, not just ideal gases. We write the following. We give this a value, right? This partial derivative we'll call psi of T. It's known as the internal pressure. It must have units of joules per meter cubed. Why? Because it's an incremental change in energy with respect to a change in volume. Standard units of energy, the joule, named after James Prescott Joule, divided by the standard units of volume, don't forget meters cubed. Not equal to 1 liter. They differ by a factor of 1,000. Which one's bigger? Okay, so we proved that later on, and this will be probably 3 lectures, maybe 2, that an expression can be evaluated for the internal pressure, which is equal to the temperature times the partial derivative of P with respect to T at constant volume minus the pressure. Why is this a useful expression? It's general, but it's only good if we can actually measure the quantity that's the partial derivative or get it from something else. Where would we get that partial derivative? From where? From the equation of state. We have the equation of state, we can evaluate that partial derivative. Okay, so there will be a problem on the homework where you have to do that. Using this expression for the internal pressure. Okay, so we'll go ahead and do it for an ideal gas. All right, so we know for an ideal gas that that partial derivative has to be 0. So if that expression is a general one, then it has to work for an ideal gas. It better give me 0 or it's not right. Okay, so we can evaluate the partial derivative of P with respect to T at constant volume. That's easy, right? Since P is equal to nRT over V, then holding everything constant except taking the derivative with respect to temperature just gives me N over R. Okay, so now I plug that in. And so nR over V is plugged in for the partial derivative of dP dt at constant volume. Multiplied by T, and then it's easy to show that that's just the pressure, nRT over V. And so it's the pressure minus the pressure, that's 0. So this works for an ideal gas. Assuming that you have an expression for the equation of state, right? And we've looked at 4 of them so far. We've looked at the ideal gas law, the van der Waals equation of state, the Pang-Robinson equation of state, and the Redlich-Kwong equation of state. We could evaluate the internal pressure for each of those. And if we wanted to evaluate what the dependence of the internal energy was on the volume, then we would need to know the equation of state in order to get numbers. But this expression works for any equation of state. Okay. So this is exactly what we expected for an ideal gas where the internal pressure is equal to 0. Okay, so now internal energy, we need our general expression. So for this one we plug in CV, and for that one we plug in our symbol pi of t. Okay, and I'm go ahead and plug in the expression that I had for the internal pressure here. This is a useful one because we can always evaluate that depending on the equation of state, and then we can integrate each of those and obtain a change in internal energy or a change in volume and temperature. All right, so now that's the general expression. Or if we want, we can dispense with the expression here and use the quantity for the internal pressure. Sometimes these are table values, but usually you have to actually evaluate them from that expression. Okay, so then for an ideal gas, du is equal to CV dt because the internal pressure is 0. Okay, not once in the entire discussion have I said that this is at constant volume. That expression works whether you're at constant volume or not. For an ideal gas, that's true always. We kind of knew that already because that's something that we knew from the kinetic theory of gases. We knew that if we wanted to change the energy of a gas, we had to change its temperature. But that was a gas of atoms. It's true for every ideal gas. Yes?
It's because W is a state function?
It's mathematically that's where it came from. Chemically, it's true because we're not accounting for any other energy other than energy of translation. For an ideal gas, we assume that there's no interaction between the particles. So when we start dealing with interactions between particles, we no longer have an ideal gas, and there the internal pressure is non-zero, and we have to actually calculate it from that expression above. So true always for an ideal gas. All right. So now, how to build a better mousetrap. How to do the Joule expansion experiment better. Okay, so Joule, as we know, worked in the family business. He brewed beer in the brewery near Manchester. Okay, at the time, mid-19th century, the only way to communicate your findings were two ways. Either you could convince somebody that you were right and have it published, and that circulated as books, that was fast. Joule had real trouble doing this because he had no credentials. He had no formal training as a physicist. He had no education. He could not convince the scientific hierarchy that his experiments were right. Okay, so he tried to convince everybody he could talk to, and his work became known by someone who did have credentials, a professor of physics at the University of Glasgow in Scotland, William Thomson. William Thomson, born in Ireland, in Ulster, but is considered a Scot. He spent most of his career at the University of Glasgow, and he was a professor of physics. He became the first Baron Kelvin. So this is Lord Kelvin. So William Thomson and Lord Kelvin are the same person. Okay, temperature scale, Kelvin, the Kelvin-Planck formulation of the second law of thermodynamics, what you'll hear. This is all William Thomson. But in this experiment, which is in 1852, was a better way of looking at expansion from a region of high pressure to low pressure and calculating the change in temperature that occurs due to that. Okay, and so Thomson was aware of Joule's work, had many discussions with Joule, and they together devised this new apparatus to make these measurements. Okay, so here's how it works. In this experiment, gas is allowed to expand freely through a porous plug or a frit. Okay, and why a porous plug? This is the throttle. Okay, so you have to be able to measure, you have to be able to change how fast the expansion occurs because you're assuming that this is a reversible transformation, even though you're expanding into what is essentially a lower pressure from a higher pressure. So you know that that would happen spontaneously if you just opened the valve. Okay, so the porous plug acts as a throttle. Okay, so here's the initial condition. We have one side, here's our piston with gas inside of it at pressure P1, V1, and T1. So we're representing the pressure as this mass weighing down on our frictionless, massless piston. And then we connect these two pistons with a porous plug, and in this piston we have no gas. Okay, so our piston is just sitting on top of the bottom of the cylinder, and it's being weighed down by mass 2. And then everything is encased in an adiabatic wall. So in other words, the porous plug is also insulated. Both pistons are insulated. No heat can be released. And so we have to be able to measure the gas. We have a thermometer inside both pistons to measure the temperature. Okay, so then this is done at constant heat, under adiabatic condition, as we isolate everything. Okay, so now we open the valve. And so we have no pressure over here. This pressure has to be lower than this pressure. Okay, so P1 is going to be lower than the final pressure P2. So this will, once we open the valve, all of the gas will go to the other side. So then the volume will be bigger on this side. So we open the valve, and this happens. Our gas throttles over to this side. And then we have all the gas on this side, and none on this side because this weight is smaller than that. Okay, so now we have gas at P2, V2, and T2. We can determine the changes that occurred in this transformation. Okay, so the quantity we really want is the change in temperature, T2 minus T1. So for piston 1, our initial condition is V1, and so what happens inside here is we go from a volume V1 to 0 here, and then we go from pressure P1 to 0. So the work here, which is done, we are assuming under equilibrium conditions. So the gas inside here is equal to the pressure that's pushing down on it. So the work done is just equal to P1 times V1, right? The work is minus P delta V, and delta V is minus V1. So it's positive, and that makes sense because work is being done on the system by the mass pushing down and compressing the gas. And then work in this system is doing PV work because the gas expands from 0 volume to V2. Okay, so here we have a quantity of work equal to minus P2 V2. And the throttling mechanism assumes that we're doing this reversibly, which is why we can say the external pressure and the internal pressure are equivalent. So you have to do it slowly, and that's why you throttle the gas. You can actually set this up. Google Joule-Thomson cooling, and you'll see a few people's apparatus to do this experiment. It's kind of cool, I get it. Anyway, so what happens here? All right, so what happens here is you measure the temperature difference. And since this transformation is done under adiabatic conditions, we know some specific things about delta U and delta H. Okay, since the first law of thermodynamics says that delta U is equal to work plus heat, and heat is equal to 0 under adiabatic conditions, the work is equal to delta U. Okay, well, we know what the work is. The work is the work of piston 1 plus piston 2. Our system is both pistons. And then we know what this is because we derived this on the previous slide. For piston 1, our work was positive, and it was P1 times V1. And then it was negative on the other piston, minus P2 V2. Okay, well, that would mean that our delta U is equal to P1 V1 minus P2 V2. But we know that delta U is just the internal energy of the first piston plus the internal energy of the second piston, which is the final condition, minus the internal energy of the first piston, which is the initial condition. Right? Our initial condition is all gas in piston 1, none in piston 2. And then our final condition is all the gas in piston 2, none in piston 1. Okay. So now we get 1s on one side, 2s on the other. So we do algebra. And we know what U plus PV is. That's just the enthalpy. So really what we have here is we have enthalpy in piston 2 is equal to the enthalpy in piston 1. So in other words, by opening up that valve, we haven't changed the enthalpy. So if these are equal, then delta H is equal to 0, and this is isenthalpic. So like the Joule experiment, where he didn't measure any temperature change, so he assumed constant internal energy, even if we measure a temperature change in the Joule-Thomson experiment, we have constant enthalpy. So these are under constant enthalpy conditions. So now we'll go back and look at enthalpy. Okay, so at the beginning of lecture, we said we want enthalpy as a function of temperature and pressure. So here's the partial derivatives. You've seen this equation before. Okay, so if we assume constant pressure conditions, then the last term goes away, and we have that the change in enthalpy is really equal to the change in the constant pressure heat, right? We knew that. That was why we defined enthalpy. And now from the above expression, this is equal to Cp dt. And like before, this has to be equal to the partial derivative of H with respect to T constant P. Okay, so this was from our original definition of enthalpy. This one was from our definition of heat transactions at constant pressure. And then the last one comes from setting P equal to 0 here. And so this means that Cp is equal to the partial derivative of H with respect to T at constant pressure. We already knew this, but again, this is a formal proof. Okay, so nothing new yet. Okay, so it's this term, right? That term is the one we're going to get from the Joule-Thomson experiment. Again, the Joule-Thomson experiment measured the change in temperature with respect to a change in either volume or pressure, right? And we know that both the volume and the pressure changed. So if we just assume that it was measure the temperature with respect to a change in pressure, going from one piston to the other, at constant enthalpy, then we have a shot at getting that derivative through an Euler chain. Okay, so using what we know from the Joule-Thomson experiment, we can obtain an expression for the pressure dependence of the enthalpy, in other words, this partial derivative. Okay, in the Joule-Thomson experiment, this resulted in a measurement in the change of T with a change in pressure at constant enthalpy. Okay, and we'll define this as the Joule-Thomson coefficient. Okay, so this is given symbol U. For an ideal gas, this is going to be 0. We'll come back to that. Right, so nothing funky is going on here for an ideal gas. This Joule-Thomson coefficient is non-zero if we are assuming interaction energy between the gas particles. Okay, so in order to obtain the desired expression, which was dH dP at constant T, we can use an Euler chain. Same way we did for du dV at constant T. And so we set it up with the one we want, which is, we want this one, because this is the one that goes into our expression for the total derivative of H. And then we start our Euler chain here. So P goes on top, T comes in, H goes to the bottom. And then T goes to the top, H goes inside, and P goes to the constant variable for the third term. And this is equal to -1. Okay, this one here, that's going to be Cp, or this is 1 over Cp. This one is going to be the experimental measurement of the Joule-Thomson coefficient. And so we'll get our expression for dH dP at constant T. All right, so how do we do that? We divide and then invert. So this is the Joule-Thomson coefficient U, and this is the heat capacity at constant pressure Cp. Okay, so usually they're combined, and then the Joule-Thomson coefficient is written as mu of T, and this is called the isothermal Joule-Thomson coefficient, which is why you have sub T. And you'll see that value tabled as well as the Joule-Thomson coefficient mu. Okay, so now we have an expression for both dH dt at constant P, that's just Cp, and dH dP at constant T, that's mu of T. And so now we can plug those into our our exact differential for H. So this is what we had before. H is a function of T and P. And now we know what each of those are. Okay, so here I actually used the Joule-Thomson coefficient and the heat capacity at constant pressure. Okay, so now we go ahead and we look at the quantity for an ideal gas. And I mentioned it already. It's been shown twice in the lecture notes that this quantity is equal to 0. I'm going to prove it. So for an ideal gas, I'm going to prove dH dP constant T is equal to 0. Okay, so previously we proved this one. Right? We had an expression for the internal pressure, and we showed for an ideal gas this is equal to 0. So I'm going to make use of this. Okay, so now using the chain rule, this is not an Euler chain, but this is a chain rule, we'll differentiate U now with respect to P at constant T, and then P with respect to V at constant T. And since that's just equal to this partial derivative, this product also has to be equal to 0. Okay, then for an ideal gas, we can evaluate dP dt, and that's why I did this. Sorry, dP dV. So we can evaluate this one using the P equals nRT over V. And so that derivative is equal to minus nRT over V squared. Now I can plug that in for the top quantity. Okay, sorry, this is plugged in for this value here. So this means that since these are non-zero at least some of the time, and this is always 0, that this guy has to be 0. Okay, so now we not only know that du dv at constant t is equal to 0, but we know that du dp at constant t is equal to 0. And now I think you can see where we're headed, right? Now we can use our definition of enthalpy, solve for u, plug that in this partial derivative, and go ahead and take the derivative. So let's do that. So the definition of enthalpy is U plus PV. So this is what we want to show. Now we're still talking about an ideal gas. So we can just plug in for enthalpy U plus PV. Now we can take this partial derivative. So we have du dp at constant t. We just showed that's equal to 0. And now we have dp, or d of the quantity PV, and taken with respect to P at constant temperature. Okay, so for that term, we have to use the product rule to do the derivative, right? So we hold one of the variables constant, take the derivative of the other. So the first term is going to be P times the partial derivative of V with respect to T, respect to P at constant T. But then when we hold V constant and we take the derivative of P with respect to P, that's just 1. Okay, so let's do it. All right, so now for an ideal gas, we can actually evaluate that partial derivative because we can solve for V as a function of P and T. So PV equals nRT means V is equal to nRT over P. We take that derivative with respect to T to P holding T constant, and it's minus nRT over P squared. So now we're going to plug this into here, multiply by P. And you can immediately see that P times 1 over P squared is 1 over P. So this becomes minus nRT over P, which is the same thing as minus the volume. So this whole quantity is going to be 0. That partial derivative we just showed was 0. The whole thing's going to be 0 for an ideal gas. But let's go there. Okay, so same expression we had at the bottom of the previous slide. And then we go ahead and distribute our P into that parentheses, and it's minus nRT over P. And so that's just the same as minus the volume for an ideal gas. And so this term goes away, and then dH/dP at constant T is the same thing as du dP at constant T for an ideal gas. And since we showed that du dP at constant T is equal to 0 for an ideal gas, therefore dH/dP at constant T is equal to 0 for an ideal gas. And what does that get us? That means that for an ideal gas, this is general, right, for any gas. But then when we go to, and this is general for any gas. And then for an ideal gas, that quantity is equal to 0. So that for any ideal gas, dH is equal to Cp dt. Notice that not once in any of the discussion regarding the enthalpy did I hold pressure constant. This is true always, regardless of whether pressure is constant. Okay, so for an ideal gas, these are, for an ideal gas, the change in internal energy is equal to CV dt, and the change in internal, or the change in the enthalpy is equal to Cp dt. If we have a real gas, then for the internal energy, we'll need the internal pressure, or du dv at constant T. And for the enthalpy, we'll need the partial of H with respect to P at constant T. But we don't need it for an ideal gas because each of those are 0. All right, so now for a real gas, we showed this for enthalpy. Okay, so for any real gas, this is not guaranteed to be 0. It might be very small, but it's not guaranteed to be 0. So what does this do? What does this mean? Okay, so that's where I'll give you some physical insight here. So the Joule-Thomson coefficient mu is in general non-zero for real gases and can be positive or negative. So if we consider the Joule-Thomson experiment described previously, where pressure 2 was less than pressure 1, then what was measured here was this quantity, the change in temperature with respect to pressure at constant enthalpy. Then, if our Joule-Thomson coefficient is less than 0, then the change in temperature is greater than 0, and this leads to heating. Vice versa, if mu is greater than 0, if it's a positive value, then delta T is less than 0, and this leads to cooling. And so most of the knuckleheads doing this experiment and you gotta Google it because it's really funny, some of the apparatuses they're using to do this. Apparati, I suppose is the right way to say it. But they're compressing air, right? So you can easily do this using an air compressor. You can put you feed air from the room into the air compressor, and then you increase the pressure inside the air compressor to 100 atmospheres. And so that's P1. And then you expand it into the regular atmosphere, which is at 1. So that's 2 order of magnitude change in the pressure. And so that expansion into the room will actually cool down whatever you expand into.